Thank you everyone for joining us today for our seminar. It is my pleasure to introduce our speaker today, Dr. Ananya Mallik. Ananya is a faculty member in our department, an assistant professor. She obtained undergraduate degree and a master's degree in geology at Jadavpur University in Kolkata in 2006 and 2008. And after that, she moved to Rice University to work with Raj Dasgupta in experimental petrology and geochemistry for her PhD. So upon completion of her PhD, she moved to Bayreuth in Germany as a postdoctoral fellow. And for between 2016 and 2018, she held a prestigious Alexander von Humboldt postdoctoral fellow, also at Bayreuth. After that, she moved back to the States in 2018 for a short postdoc at Brown before she was tapped by University of Rhode Island and hired as an assistant professor. She was there for 1 year until we were lucky enough to hire her at University of Arizona. And she's been here since, I guess that would be the second wave of the pandemic. So like July of 2020. Where she's an assistant professor and has an endowed position from the Real Inc. in Geosciences. So since Ananya arrived here, she's been working hard on getting the track for Geosciences up and running, and building an experimental geochemistry and petrology laboratory downstairs in the basement of Gold Simpson that I'm lucky enough to share a space with Ananya. And her interests are really varied. She works, her main interest is to try to understand the geochemistry and petrology of planetary mantles. She focused a lot of her PhD work on understanding the reactions between melts and peridotite in the mantle. And her more recent interests are in understanding fluxing and recycling of volatiles in the mantle, and now trying to understand the petrology of the moon, which is what she's going to talk about today. So with that, I'll hand it over to Ananya, and the floor is yours.
Thank you, Mauricio, for the introduction. So yes, I will be talking about this sort of my recent research that's going on in planetary sciences, mostly focused on the moon. Okay, so the title of my talk is really simple, and it's exactly what I'll be talking about. So how hot and wet is our moon, and what can we learn from experiments about that? So I would like to acknowledge my co-authors in these projects that I've been working on. And especially I would like to highlight the work of Arkadeep Roy, who is a graduate student in our department. And how wet is the moon is actually part of his doctoral thesis work. And then also Pranwendu is involved, who's also affiliated with our department here. So basically this talk has two parts. The first part is about how hot the moon is. And the second part is about how wet the moon is. So let's start with how hot the moon is, and what do we know about the thermal state of the moon, and how can we constrain it better? So Jess Barnes gave a talk a couple of weeks ago, and she gave a really nice introduction about what's the importance of studying the moon. So I'm just going to briefly go over it again. As we all know, that there was a Mars-sized body called Theia that basically hit the Earth, and then everything vaporized, and then this silicate vapor formed a rotating donut, also known as a synestia. And then eventually, from this silicate vapor, the moon and the Earth formed. And so given the fact that the moon and the Earth have a common origin, and the moon is our closest neighbor in the solar system, studying the moon can tell us a lot about the origins of our own planet. And this is what sparked a lot of interest in lunar science. So the first question is, how hot is the moon? Now, as we know that from this giant impact, which generated a lot of heat, and when the moon was formed, a substantial fraction of the moon was actually completely molten. It had a magma ocean. And then, that magma ocean cooled down, it crystallized different minerals, and that's how basically the solid body of the moon was formed. So here we have different models of what the moon's interior must have been after magma ocean crystallization. I would point out that all of these models are either derived from experimental petrology, where lab experiments were done to simulate that if you crystallize a magma ocean, what sequence would you form? And some of these models were also derived from thermodynamic modeling. This here is basically a sequence that's sort of stitched up. So the upper half is from the Snyder et al. Study right here. And then the lower half is from the Alardo study, which looks at the lunar lower mantle right here. So one common thing about all of these is that most of the moon's mantle is basically comprised of the minerals olivine and orthopyroxene, which are also the two abundant minerals that we have in the Earth's mantle, the Earth's upper mantle. And so that tells us that the moon's mantle is not very different, at least from the Earth's upper mantle. But of course, there are some differences. So this, if you go from the bottom to the up, this is basically representing the percentage of crystallization. So the more you crystallized, the more enriched you got in certain elements. So for example, in calcium, aluminum, and so on. And so at some point, you would saturate plagioclase, and the plagioclase basically formed a flotation crust on the moon. And then at the very end of the magma ocean, the last, let's say 10% or so, that residual magma ocean was very enriched in iron and titanium. And so that formed an assemblage, which was actually a very iron and titanium enriched assemblage. And that assemblage, this is the layer right here, also happens to have a high density. But I'll come back to that point later on. Okay, so what we know is that after magma ocean crystallization, about 4.5 billion years ago, we have an idea of what the interior structure and composition must have been, because we know that from experimental work and from thermodynamic modeling. But then the question is, what is the moon's interior today? Has the interior evolved since magma ocean crystallization? And really, in order to constrain the interior structure and composition of the present day moon, we need to constrain the thermal profile of the moon really well. So this figure right here, this is temperature versus depth, and this gray zone actually shows the range of temperature profiles that we know about the moon today. And all of these are inferred from basically seismic and gravity data inversions. So you can see there's a wide range over here. So this is the surface of the moon, and this is all the way down. So this is close to the core mantle boundary of the moon. The blue line here represents the minimum selenotherm. So for those of you who are not aware of, or you're not used to the term selenotherm, it's basically the equivalent of geotherm for Earth. So it's equivalent of geotherm on the moon. That's what it is. So you have a cold selenotherm, you have a hot selenotherm represented by this red line right here. And then, you can have a mean selenotherm right here. But it's a wide range. I mean, if you look at the range here near the core mantle boundary, it spans about 750 Kelvin or more. Now, the point is that in order to actually constrain the interior composition better, the choice of selenotherm really matters. So here's sort of a result from this other study that I'm involved in. So these are the different layers of the moon that we started with. And then what we were trying to see is that which internal configuration, so which layer thickness combination would best match the mass and moment of inertia of the moon today. So this here is basically the z-score, which is nothing but a deviation from the actual mass and moment of inertia of the moon. So the lower is the z-score, the better a match it is. And then these here are our top 30 models based on the z-score estimates. And as you can see, these diamonds here represent that at which selenotherm were these internal configurations modeled. And you can see that there's a color variation, which means really the choice of selenotherm matters as to what the internal configuration is. And this highlights the importance of constraining the selenotherm well for our current moon. In fact, at the Lunar and Planetary Science Conference, which happened a few weeks back, it came out of one of the session discussions that perhaps one of the frontier questions right now in the lunar science community is to actually constrain the lunar selenotherm better. So of course, then the question is, how can we constrain the selenotherm better? What can we do about it? And before I go into some experimental studies that I did to contribute towards determining the selenotherm better, I thought I'll talk about two observations that we have from the moon on which the study is based on. So here's the first observation. There were different pristine lunar glasses that were collected from the moon in these Apollo missions 12 through 17. So this is TiO2, titanium dioxide versus iron oxide. All these gray points are basically terrestrial samples, so terrestrial ocean island basalts, mid-ocean ridge basalts. And all these colored samples right here are basically these lunar glass samples. As you can see that they are very distinct from the terrestrial ones. A, they have much higher iron concentration. B, some of them have very high titanium concentrations. And so they're kind of weird if you compare them to the terrestrial basalts. And so the question was like, where on the moon and how on the moon could they have been formed? And understanding the source depths of these lunar basalts, this is something that Tim Grove at MIT has been doing for several years now with many of his students. So this graph here is this figure here is something that Mike Krasinski and Tim Grove published in their paper in 2012, where they actually, using multiple saturation experiments, they were able to determine the possible source depths at which these glasses must have formed in the lunar interior. So here you can see, these are the Apollo red glasses, the red glasses right here, the black glass, and so on. So the thing to notice is that all of these lunar glasses are actually sourced from within even a few hundred kilometers inside the lunar mantle. So now, of course, the question is, how do you have some iron titanium enriched source at those depths inside the lunar mantle? Because if you recall again, going back to these figures, if you look at the lunar magma ocean crystallization sequence, the only iron titanium enriched layers were at the very top. There isn't really anything here that would explain the iron and titanium enrichment. And this is when this other concept came in, which is that this iron titanium enriched layer that resides just below the flotation crust, because of its high density, it actually sank deep inside the moon because the density is higher than the underlying mantle below. And this is what we call the lunar mantle overturn. If the lunar mantle overturn was efficient, then ideally all of this layer would be sitting right at the core mantle boundary, but in reality, it may not be 100% efficient. In that case, we can have these iron titanium enriched lithologies scattered throughout the moon's mantle, and that could maybe contribute to the source of these high iron titanium glasses that Tim Grove and his group have studied. Okay, so the second observation that we have, and this is from seismic data from the moon. So the Apollo missions planted 4 seismometers on the near side of the moon, so we have some seismic data from there. And inverting that seismic data, so this is a study that came out in 2011, led by Renee Weber. So this is velocity versus depth. And these are the S and P wave velocities. And what they observed was that there's a slight dip in velocity near the core mantle boundary of the moon. The other observation was that they noticed a very sort of distinct absence of moonquakes on the far side of the moon. And so their interpretation is that, given the fact that the far side quakes have not been detected and that there is this slight dip in velocity near the core mantle boundary of the moon, that means there must be like a mushy attenuating layer sitting at the core mantle boundary of the moon. So a partially molten layer, that's what they mean. So now, the question is that could this iron titanium rich layer, which sank deep inside the moon as a result of this overturn process, could this actually be responsible for this partially molten layer that's sitting at the core mantle boundary? Now, in order to test this hypothesis, we would need to investigate the partial melting behavior of this iron titanium rich layer right here. And then can we use that partial melting behavior to constrain, let's say, the core mantle boundary temperature? Because if we constrain the core mantle boundary temperature, that will be a boundary condition for a lunar selenotherm. So in order to investigate the partial melting behavior of these iron titanium rich lithologies, we did some experiments. So we basically synthesized two different compositions. One here is basically the composition of that iron titanium rich layer that we expect to have crystallized from the lunar magma ocean. And then what we did was we mixed some mantle with it to basically make another starting composition. So that was the iron titanium rich layer mixed in with some mantle, let's say. And then the experiments were done using what we call a multi-anvil device, which is basically this gigantic hydraulic press. This is actually in Bayreuth, Germany. What this gigantic hydraulic press can do is it can go to very high pressures and also high temperatures that can be explored in the lunar interior. So the particular press that I had used is actually not this one. It's a slightly smaller version of it. But nevertheless, I was able to go up to 4.5 gigapascals of pressure using that smaller version of the multi-anvil. So basically the experiments were done at two different pressures. One is at 2 gigapascals, and this range of temperature, 2 gigapascals is about the depth that one would expect for the source of these lunar glasses with different titanium concentrations. And 4.5 gigapascals, that would be pressure close to the core mantle boundary of the moon. So what we do in these kinds of experiments is we take our starting material, the one that I talked about before, we have it in the form of a powder, we put that in a really tiny capsule, and then the capsule goes inside a bunch of refractory material spacers, and then this graphite furnace, this black thing here, and then this whole thing goes inside this magnesium oxide octahedra, and then this is surrounded by tungsten carbide anvils. And then this whole thing will actually go inside the press. So what happens is the press has rams that would pressurize these anvils, and then these anvils would transmit pressure to this octahedra with the sample inside. And then this graphite furnace around it, what we do is we basically run electricity through it to heat up the sample at our desired, temperature conditions. And so at high pressure and temperature, we cook these samples for, it depends, maybe 24 hours, 48 hours. And then we basically shut off the electricity. So we quench the samples, hoping that the quenching would preserve the samples as they were at high pressure and temperature. And then we retrieve the quenched samples and we polish them, and then we do all kinds of analysis. So this is how we do these high pressure temperature experiments. In this case, simulating conditions inside the moon. Okay, so just to show you some results. So here I have two images of experimental samples after they're cooked and polished. And so what exactly do we see in them? So this one here is just that high iron titanium composition that crystallized from the lunar magma ocean. And this here is a mixture of that high iron titanium composition with the lunar mantle composition. And so these were done in a graphite capsule. So you can see graphite around it. And then you see glass here, and then different minerals. So this one formed augite, which is a kind of pyroxene. Then there was glass, there's quartz, and then there's also iron metal. Here we have olivine and orthopyroxene in these gray zones here. And then here, basically, the melt that was a liquid at high pressure and temperature, that melt quenched to a glass in this case. But here, it didn't really quench to a glass. It quenched to something we call like a quench mat. You can see these quench crystals in there. And then we also had iron metal. So from these different experiments, we can actually calculate the proportions of all of these phases using mass balance. And then, once we know the proportions of these phases, especially the proportion of melt that's forming in these samples, we can plot up temperature versus, let's say, melt fraction. And then, we can extrapolate that to where, the melting would have just initiated. So let's say close to 0% melting, which is where the Solidus temperature would be. And so that's exactly what we did here. So these are the two curves. These are the two Solidus curves for these two compositions. The red one here is basically the Solidus curve for that iron titanium composition that we expect to have crystallized from the lunar magma ocean. And the blue one here is that same composition mixed into the mantle. For reference, this pink curve here is the Solidus of peridotite. Peridotite is what our Earth's upper mantle is made of. And then this green curve here is actually the Solidus of olivine with forsterite content 92. So as you can see that these two lithologies actually melt at much lower conditions than a peridotite would. So we determined the solidus through these experiments. And so the question is, if these iron titanium rich cumulates are responsible for producing that partially molten layer at the core mantle boundary, one of the conditions that needs to be met is that that particular partial melt is either neutrally buoyant at that depth or is denser than the overlying mantle in order for it to actually be stable and stay on for that long. So the next thing that we did was actually calculate what the densities of these partial melts that were produced in my experiments, what the densities would be. So for that, basically we used a Birch-Moynihan equation. And in this Birch-Moynihan equation, an equation of state where you can calculate the density at a given pressure and temperature, the inputs would be density at 1 bar, which was calculated using the composition and the partial molar volume of the different oxides, oxide components in that liquid. And then the other input would be the isothermal bulk modulus and the pressure derivative of the bulk modulus for different lunar glasses that have been derived from experiments before. Now, as it turns out that the bulk moduli actually have a range in literature. And what that means is that the output, which is the density at the desired temperature and pressure, we obtained a range in the outputs right here. So this figure, again, this is density versus depth versus pressure, pressure going down as you go higher in depth. And then this line right here, the black line, is actually the average lunar mantle density from the very preliminary reference model for the moon from Garcia et al. 2012. And these here are the density estimates for the liquids that came out of these experiments. So what it means is if the liquid density is lower than the density of the mantle, then that melt would rise. If it's denser, then the melt would sink. But right now, given the range that we see, really the melt could be doing anything. It could be rising or sinking. So we have not been able to constrain the density of these melts very well using the current bulk modulus that we have in the literature. So one of the ongoing studies we have right now is basically constraining the densities of these liquids using in situ X-ray absorption at the synchrotron so that we can get a much better handle on what the bulk moduli would be, and then we can use that to constrain the density better. But nevertheless, given the range of densities that we see, there are two possible scenarios that can happen. One is that the partial melt ends up being denser than the surrounding mantle. If that's the case, then the partial melt will be stable at the core mantle boundary. The other option is that the partial melt is less dense than the surrounding mantle. In that case, that partial melt will actually rise. And given that this partial melt is very different in compositions from the surrounding mantle, it would actually react as it rises, so there will be reactive ascent. And then this partial melt could eventually contribute to volcanism on the moon. But let's assume for now that, or let's suppose that the first case is the right one. So in other words, that partial melt that we derived from our experiments just happened to be denser than the surrounding mantle. If that's the case, then we can actually use the bracket of partial melting that was predicted by the seismic data to constrain what the core mantle boundary temperature on the moon would be. So from the seismic data, what they supposed is that for that kind of velocity dip, and depending on the melt geometry, the partial melting degree would be somewhere between 5 to 30%. So here's melt fraction versus temperature, and these are the experimental data that we have. So basically, what we can do is we can find out that what temperature range is covered by the 5 to 30% partial melt. From this figure right here. And what we see is that that temperature range happens to be about 1330 to 1470 degrees C. So if these partial melts are indeed dense and they can stabilize at the core mantle boundary, now we do have a constraint for the core mantle boundary temperature, which is given by this purple bar right here. So this is a much better constraint than what we have currently right now. Okay, so the summary so far in this part of the talk is that partial melting of this overturned iron titanium rich cumulates and their mixture with the mantle that was investigated at these two pressures and a range of temperature conditions. The estimated densities of these partial melts using their composition their isothermal bulk moduli and pressure derivative from the literature actually gave us densities that could be both higher and lower than the lunar mantle. So the fate is inconclusive right now. And that's why we have an ongoing study to constrain that better. If these partial melts happen to be denser than the mantle, then 5 to 30% of partial melt, which is predicted by the seismic studies, would stabilize between 1330 to 1470 degrees C. So this would be our constraint on the core mantle boundary temperature. And then in a future study, me and my collaborators, what we will be doing is we will be using this as a boundary condition, and then also coming up with the heat producing element budget of the moon and the distribution of heat producing elements within the moon to construct the selenotherm better. Okay, so this was the first part of the talk about how hot the moon is, what do we know, and what could we do to constrain it better. Now I'm going to move to the second part of the talk, which is how wet is the moon? How much water is there on the moon? So now the first question is, why would we be interested to even know how much water there is on the moon? And when I say water on the moon here, what I mean are endogenous volatiles. So basically volatiles that were inherited by the moon during the process of accretion. So the bulk hydrogen content, along with the D/H, the deuterium to hydrogen ratio in the bulk silicate moon, is important because it can be used to derive the dynamics of the moon forming impact. It can also be used to determine the origin of volatiles in the Earth-Moon system. So for example, will the volatiles derived from carbonaceous chondrites or more volatile depleted enstatite chondrites? So to summarize, basically finding out the nature of building blocks that form the Earth-Moon system. And of course, hydrogen has been measured in a suite of lunar samples. So these are just several examples here. They've been measured in melt inclusions hosted within olivines, in glass beads, in apatites, in plagioclase grains from lunar anoptosites, in granite clasts. And so all of these studies, they've come up with a range of bulk hydrogen or water equivalent contents of the moon, which ranges from like a few tens to several hundreds of micrograms per grams. And this is just for reference, it's similar to the estimated water content for the depleted Morb mantle of the Earth. But of course, this is much drier than what we think the bulk silicate Earth water may have been, or is actually. But what we would notice here is that there is actually, at least 2 to 3 orders of magnitude range of proposed values for bulk water on the moon. So again, the question is, can we constrain the bulk water on the moon better? A. Also, what factors does this constraining the bulk water on the moon depend on? So here's a figure from Hui et al., where they had actually measured hydrogen in plagioclase from these lunar plagioclases, basically. And in this figure, you see this is water concentration and these different materials that have been analyzed for water. So this is basically the water concentration from the ferron anoptosite samples that the study did. And then these are, so water contents that have been measured in lunar basalts, and then they inferred what the source amount, what the source concentration of water would be from which these basalts were derived. So basically, this is also basically the source concentration of water, let's say in a fan, in the plagioclase, right? And so again, when we go from measuring hydrogen in a lunar sample and basically using that to go back to what the source content would have been, there are some assumptions that go in there. And one of these assumptions is actually the partition coefficient of hydrogen during crystallization from the lunar magma ocean. So basically, this is what it is. We call it DH, mineral melt, which is the ratio of concentration of hydrogen in the mineral over the concentration of hydrogen in melt. So depending on the choice of partition coefficient, the estimates of source water concentration can actually vary. Now, when we look at the range of partition coefficients of hydrogen that have been published in the literature, what we see is that for minerals that crystallized during lunar magma ocean, there's actually a range that has been reported. So, this is the minimum range, we call it DH min, and this is the maximum range, we call it DH max. And so you can see that this range varies across an order of magnitude, depending on the composition of these phases. So for example, for pyroxenes, the more aluminum there is in the pyroxene, hydrogen tends to be more compatible in the pyroxene. Also, depending on the ion content of the phases, also redox conditions. So recently, a couple of studies actually, so this one right here, Lin et al., they estimated the hydrogen partition coefficients applicable for reduced lunar conditions, and they found that hydrogen is actually more compatible than it would be for more oxidized terrestrial conditions. And so a possible reaction, redox reaction that could be going on here is that when you reduce iron, in doing so, you basically make the hydrogen more compatible in the mineral. Also recently, another study came out by Mosenfelder 2020, where they looked at the solubility of water in plagioclase as a function of oxidation state, or FO2. So to the right, we have more oxidized states, we have more reduced conditions to the left. And here, basically, this is the amount, the maximum amount of water that can be put in the plagioclase crystal. So what they observed is that the more reduced the condition is, the more water you can put in these plagioclase, which also hints towards the fact that perhaps at lunar conditions, hydrogen would be more compatible in these minerals that crystallize from the lunar magma ocean. So one thing that we wanted to do here was we developed a proof of concept study. And in this proof of concept study, what we tried to show is that how much of a difference in bulk hydrogen content of the moon there is, depending on the choice of partition coefficient that we use during lunar magma ocean. So in this proof of concept study, so the goal was to show that how important it is to actually estimate the partition coefficients that are applicable for lunar conditions, and also the different factors on which this modeling would depend on. So some of the other factors, such as the amount of interstitial liquid that's held during lunar magma ocean crystallization, and so on. So I'll talk about all of these now. So in this proof of concept study, this is an ongoing study, I have to say, we are considering two n-member scenarios during lunar magma ocean crystallization. So one is this n-member scenario where we assume that the lunar magma ocean, which has a lot of volatiles to start with, is undergoing vigorous convection. So what happens is, as the lunar magma ocean crystallizes, as these minerals keep forming, the residual magma ocean gets more enriched in water, some species of hydrogen. It could be water, it could be molecular hydrogen. And then at some point, this residual magma ocean can actually even reach its solubility limit, at which point it would start forming bubbles, and then these bubbles would degas. So here in the first scenario, what we're assuming is that the magma ocean is convecting vigorously. And so what's happening is, even at that point when it reaches a solubility limit and it exsolves bubbles, these bubbles are basically entrained back into this convection and they're basically resorbed. In other words, there is no net degassing. This is, of course, an n-member scenario. The other n-member scenario that we will consider is where we have a near static magma ocean. And again, as the magma ocean crystallizes at some depth, it would reach that solubility limit, at which point bubbles would nucleate, and then these bubbles would efficiently degas. So we would have continuous degassing of the magma ocean as it's crystallizing. And again, this is the other extreme n-member. The reality is somewhere in between the two. And as I said, that at the conditions of the lunar magma ocean, hydrogen is likely present in two species. One is as water, in which case we would use a solubility model for water, and then the other is molecular hydrogen, in which case we would be using the solubility model for molecular hydrogen. So for now, we have some results for this first case, which is the no degassing case, and that's what I will be sharing with you. Okay, so here is sort of our main key result from this exercise. So here what Arkadeep has done is that he took this experimental study by Charlier et al., where they actually simulated experimentally what the crystallization of the magma ocean would be. So what Arkadeep did was he took the proportions of these different minerals and then calculated the densities of the phases using an equation of state to basically construct this mineral stratigraphy of what the crystallization sequence would look like. And once Arkadeep did that, we implemented the partition coefficients, the minimum and the maximum, to see that how much hydrogen is partitioned into the minerals versus how much hydrogen goes into the residual liquid. And then we sort of proceeded this partitioning as the magma ocean crystallized until the very end. So this graph here on the x-axis is the concentration of water equivalent. And then this is the radius. So again, this is the surface of the moon at the top. And then as you go down, basically the radius decreases because the radius is calculated from the center of the moon. The blue lines here represent the cumulates that formed from the magma ocean crystallization. And the red line here is basically the liquid and the residual liquid that you have as you crystallize the magma ocean and how that evolves in terms of hydrogen. You have different lines here. So the thin lines here basically represent a lower bulk starting hydrogen. So we start with about 100 ppm of bulk water equivalent. And then the thick lines here are a much wetter magma ocean with about 1000 ppm of bulk water equivalent. And then the solid lines represent curves where we use the minimum partition coefficient. In other words, hydrogen is most incompatible there. On the other hand, these dashed lines are where we used the maximum end of the partition coefficients. In other words, hydrogen is more compatible there. And the same thing happens for the liquid as well. On top here, these sort of brown lines are actually how plagioclase water content would evolve when plagioclase first hit saturation during lunar magma ocean crystallization. And what we've done here is this black bar is the range of hydrogen contents that have been measured in plagioclase from lunar samples. So we use that as sort of an observational constraint. So how much water and what partition coefficient do we need in order to match the water content in the plagioclase that we actually find in lunar samples? So from this figure, what we observe is that the water content in plagioclase is best explained if we have a higher bulk water to start with, so wetter lunar magma ocean. Also, if the partition coefficient is actually at the lower end. Now, again, this sort of contradicts with some of the recent findings where we find, where they found that actually hydrogen should be more compatible under lunar conditions. And so what Arkadeep will be doing is he will be actually doing experiments to actually find out what the partition coefficient for the moon is. And if it turns out that hydrogen is more compatible for the moon, what that means is that the lunar magma ocean must have been drier than having 100 ppm bulk water to start with. Okay, so what we also did was we used this combination of thermodynamic codes of alpha melts and also another code called SPICES to model the same lunar magma ocean crystallization, but this time we explored the effect of not just partition coefficient, but also depth of magma ocean and the fraction of residual liquid that would be left behind as the magma ocean crystallizes. So this figure right here is for a 600 kilometer deep lunar magma ocean, whereas the one to the right is for a much deeper lunar magma ocean, so about 1350 kilometers deep. On the x-axis, we have fraction of interstitial liquid, and on the y-axis, we have water content in plagioclase. And so these, the orange and the blue points represent data or our model results. And then this orange field here is basically the water in plagioclase that has been measured from some of these lunar samples. And again, what we find here is that the choice of partition coefficient is definitely important because these curves, you can see they're distinct curves for each partition coefficient that we've used, but also the fact that in order to explain the water content in these plagioclase, what we need is actually the lower end or more incompatible hydrogen. And again, as I said, that contradicts with some of the recent findings because some of the recent findings hint towards hydrogen being more compatible. So if indeed hydrogen is more compatible, all that means is that we would have to have a much drier lunar magma ocean to start with, something that has less than 100 parts per million of water equivalent. Okay, so the summary so far is that the partition coefficient of hydrogen, which is basically the ratio of the concentration of hydrogen in the mineral over the concentration of hydrogen in the melt, has to be better constrained for lunar conditions in order to constrain the bulk water in silicate moon better. And that's why we have some experiments planned to do that. The water in these plagioclases from lunar samples are best explained by the lower end of these partition coefficients. However, if these experiments show that hydrogen is actually more compatible, that means the partition coefficient is at the higher end. What that means is that the lunar magma ocean should be drier than 100 parts per million water equivalent. And in the future models, even in this proof of concept study, and once the experiments are done, we will be considering degassing of both water and hydrogen species, as I explained before. And with degassing considered, maybe a wetter lunar magma ocean could be favored, but that's something that we have to see once the models come in. So just to give you a preview of the plan that we have in our lab so far. So this is Arka, this project will be part of his PhD thesis. So what we're planning to do here is basically design experiments at different FO2 conditions, including reduced conditions, where the goal will be to basically create large crystals of interest of these cumulate minerals that we expect to crystallize from the magma ocean. And then we will also put in some platinum grains here. So the idea is that, well, platinum will suck up iron, and the amount of iron that platinum would take depends on FO2. So there's actually a calibrated oxybarometer for iron and platinum, and that we will be using to actually monitor what the FO2 in these experiments will be. And so we will be doping these experiments with hydrogen and then eventually measuring the water content in the crystals and the melt using FTIR and SIMS to obtain the partition coefficients. And then once the partition coefficients are there from the experiments, we can use that to model how much bulk water is needed to explain the hydrogen contents of the lunar magma ocean products. So do stay tuned for more exciting results. And of course, I want to acknowledge my collaborators in this forthcoming project, very exciting one. And I would highlight, so Jess Barnes from LPL and Vishnu Reddy from LPL are part of it, and also Pranavendu is a part of it. So finally, some conclusions from this talk. The moon is not bone dry. We have tens to several hundreds ppm of water on the moon, but that's a huge range. So what we plan to do is we plan to determine the partition coefficient of hydrogen applicable for lunar conditions to constrain the bulk water content of the moon better. In terms of how hot the moon is, from the first part of the talk, we see that a hotter moon is preferred. In other words, a core mantle boundary temperature of about 1330 to 1470 degrees C. And then, as I said, that we will be constructing a revised selenotherm using these core mantle boundary temperature estimates to help determine the interior of the present day moon better. So that's where I will end, and I'm happy to take questions.
All right, thank you so much, Ananya. That was really interesting. So we have enough time for a few questions. If anybody has questions for Ananya. If you have any questions, just go ahead and unmute yourselves and speak up. I can't fit everybody on the same screen, so I can't see if somebody's raising their hands. I think so. Jiva, do you have a question? Jiva, I think you're muted. If you want to click on the microphone to unmute yourself. There you go.
Okay. Okay, so what is the deuterium to hydrogen ratio of the lunar water compared to the Earth? Is it the same?
There's a range, actually. There's a range for depending on what lunar material you're looking at.
Okay.
It could be, some of them are pretty negative, some of them are pretty positive. So there is a whole range, actually. It's pretty heterogeneous in terms of D/H ratio.
So compared to the Earth, the deuterium hydrogen ratio in some cases more than the Earth and some cases less than the Earth.
Yeah.
Okay. Well, that's the range is there also in the terrestrial measurements, all measurements. Okay. And with respect to the temperature gradient, or the temperature profile, how the gradient compared to your isentropic gradient? Has anybody done that?
So these are basically conductive profiles.
Conductive?
Yes, yes. So right now on the moon, we do not have any evidence of any sort of convection going on.
Yeah.
And so the assumption is that the thermal profile of the moon is basically conductive.
But you show the convection cycle in the magma.
That's in the lunar magma ocean. So
Magma
when we had
ocean,
the
okay.
magma ocean, right?
Okay,
And now it's a big question as to, like, of course, when the magma ocean was convecting and then the magma ocean cooled down and crystallized, but then how long did the lunar mantle convect after that and then switch to this conductive mode? So that's again an open question, the thermal evolution of the lunar interior.
Is there any measurement on things like pyroxene on the deuterium to hydrogen ratio?
Yeah, so actually, I can see. Yeah, go ahead.
Now, how does that compare to the Earth? That specifically pyroxene or olivine?
Pyroxenes, okay.
Olivine is a better thing, probably. Pyroxene also, but it's easier to measure in pyroxene.
So there have been measurements of D by H on several lunar samples.
Okay.
I don't have a figure with me right now, but maybe what I can do is I can maybe send you a paper, or I can discuss this with you separately. There are measurements. I cannot remember exactly off the top of my head what the particular D by H values for each of those measurements were, but it has been measured, yes.
Okay. Any more questions for Ananya? Okay, I have a couple. So one is, so when you're doing the partial melting experiments at high pressure and just taking the the iron titanium rich, like residual layer that is, presumably sinking and is partially melting. So you were trying to test whether, those partial melts are denser and are going to sink, and kind of explain the, kind of the velocity decreases near the core mantle boundary. But I was wondering if they seem to be right at the pressure at which the Grove and Krasinski experiments infer that the partial melting for the basalts that are exposed on the surface were actually generated at. So do the compositions of the partial melts that you generated match in any way, or like how do they compare with the basalts that are exposed on the surface? And is it a pure, iron titanium rich lithology partial melt a better match, or the mixture with the lunar mantle, the 50-50 mix?
With the picritic basalts that we see on the surface?
Yep.
So definitely the mixture of these iron titanium cumulates with the mantle is a better match because we have more magnesium in there. So that the magnesium really helps. But then when we look at just the iron titanium rich starting composition, so just the cumulates that crystallize from the magma ocean, those partial melts are very rich in iron and titanium. And they also don't have much magnesium in them because there isn't much magnesium in the starting material. So if those liquids somehow happen to be less dense and they basically ascend through the lunar mantle because of the lower density, they would be reacting with the lunar mantle, and that's how they would be gaining the magnesium in them.
Mm-hmm. And then that resembles the glasses that have been sampled on the surface.
Yeah, okay. We can actually reproduce quite a bit. Yes.
Great.
Elements.
All right, I see that Jess is raising her hand. Go ahead, Jess.
Hi, can you hear me? Oh yeah, okay, it's working. Great talk, Ananya. The figure that you showed with the convection and degassing versus no degassing, I wonder, have you thought about the effect of having an atmosphere early on during the lunar magma ocean, how that might affect, not just D to H, but the water content that's left, and if that can drive any oxidation or not, or if it might affect the compatibility or solubility, at least, if you're not able to efficiently lose water. Anyway, just your thoughts on having an atmosphere versus not.
Yeah, that's a great question. So yes, the atmosphere could have an impact. And you said that with an atmosphere there, maybe we wouldn't lose as much hydrogen as we think we would, which is why we have this sort of two strict end members. One is where we lose nothing, and one where we lose efficiently. So the reality is somewhere in between. So having an atmosphere would be somewhere in between the two end members. Yeah, but again, this is something I think we can think of more scenarios. I think once we have the experimental data, we can think of more scenarios that we can replicate once the data is there to figure out different, dynamic conditions, I would say.
Great, thanks.
Any more questions? Okay, I have one more, and so that it kind of like relates to linking the two parts of the talk. So like the first part of the talk, you're trying to calculate the salinotherm by like calculating the solidus of these lithologies at high pressure, and then the second part you just showed how there's a big range in the water contents, and like water, like as like has a big influence in like solidus temperature. So does the uncertainty on the water temp? So two questions. One, I assume that the first part, like all your experiments were dry, or did you add any water to those experiments? And then the second part, what's the kind of the range? Does the uncertainty in the water content affect significantly the constraints in the salinotherm based on the solidus temperature?
Yeah, that's a great question. So the first piece of good news is that our experiments are never dry. We always have some moisture absorbed in the experiments. So, the last time I did experiments in Houston, which is of course a super humid place, but then we did have air conditioning in the lab and everything. Even though I did not add water, even though I kept my samples in the drying oven all the time, I still ended up with, I think, 0.2 or 0.38% water in a glass. So what we say is that our experiments are nominally anhydrous. They're never fully dry. But going back to your question, so once we know what the hydrogen content of these cumulates would be, they wouldn't be a lot. So like right now, from the modeling exercise that we did, these cumulates would probably have a few parts per million of hydrogen in them. In theory, yes, that would depress the solidus, but I think the extent to which the solidus would be depressed is already within all the other uncertainties that we have here. So it wouldn't be anything remarkable, if that answers your question.
Yeah, that does. So you think it's essentially impossible to do an experiment that is nominally anhydrous?
Well, all the experiments are nominally anhydrous. I think
like,
it's possible to do one which is like
truly anhydrous.
Right, yeah. I don't know if Jiba's ever tried doing one experiment, like, where you try to minimize water as much as possible. I'm sure Tucson is easier than Houston, given the fact that it's so much drier here.
You can do, we have done that. That is, you have to have a kind of plastic box, inside which you load the sample, and the box is filled with argon.
Okay, yeah, with an argon.
We have done anhydrous melting experiments like that.
Yeah.
With a glove. I have in the lab, I used to have a box like that.
Oh, you had a glove box, okay.
Glove box, I had somebody threw it away, as usual. I had a glove box, and you can load the sample, and you can do the nominal anhydrous.
Yeah, so it would require like special investment, to get.
We have to evacuate the glove box and slightly, and fill it up argon or something, inert gas, and then do it there.
Yeah. So that's what we use, for example, for loading our capsules when we don't want nitrogen in them. Because again, there's so much nitrogen in the atmosphere that you have to make up these special techniques to basically avoid having any nitrogen in your sample if you want to make a nitrogen-free blank. Yeah.
The reason I was asking the question about the deuterium to hydrogen ratio, that is, if moon is formed from the Earth, you will expect the similar or higher deuterium to hydrogen ratio. Higher because some hydrogen will preferentially degas, be lighter, but not lower. So the range of values should be similar to the range of values in the Earth, which is about 4 to 6 times the solar deuterium to hydrogen ratio.
Right. I think like right now, what we know about D/H ratios from the lunar samples is that it's very heterogeneous.
Oh, it will be heterogeneous.
Yeah, it is very heterogeneous. And so one thing is explaining the heterogeneity in D/H ratio in all these samples, and then of course coming up with the bulk value in itself. Yeah.
Well, there's a measurement problem. All these things are very difficult to measure.
Yeah.
Due to hydrogen tertiary in minerals.
Yeah.
Okay, any more questions for Ananya? We have a minute or two, so time for
okay,
maybe one
Mauricio,
more question. Yeah,
I would like to correct your pronunciation.
Yeah.
The name is Ananya.
Oh, okay, right.
Not Ananya.
Okay, say that again.
It's spelled, it's correct, Ananya.
Okay.
That's the pronunciation. So,
all right, I'm not going to try that now. I'll practice on my own and then give it another swing later on. I don't want to embarrass myself anymore.
Thanks, Jiva, for saying that, but I'm okay with Ananya. It's fine. It's, you know, it's a Sanskrit.
But before you came, George Girls asked me, have you met Ananya and met whom? So,
all right. Well, I guess if we don't have any more questions, let's thank our speaker again. Thank you so much, Ananya. And and I think Kao posted a link on the chat for Diane's College of Science lecture later on today. So please do check that out